the natural logarithmic function here, integration. The previous section we talked about the differentiation process for the logarithmic function. Now we discuss here the natural log, the integration of it. The theorem, let u be a differentiable function of x, and so the integral of 1 over x dx is the natural log of the absolute value of x plus some constant c. Or if u is a function of x, then number 2, the integral of 1 over u du is the natural log of the absolute value of u plus c. So 1 and 2, very similar. You notice that in the trigonometric functions, some of the integrals are based on natural log. Now I'll take one just to highlight. Well, the sine, the integral of sine is just negative cosine. The integral of cosine is just sine. But what about the integral of tangent u du, which is negative natural log of cosine plus a constant? And then likewise with the integral of cotangent, the integrals of secant and cosecant. Let me just highlight the integral of the tangent here. So here we have this integral of tan u du. Now we know that tangent is the sine function over the cosine. So here, if we let u equal to cosine u, du, the derivative of cosine is negative sine u. The derivative of u is the du. So negative du can represent for us the sine u du. Took my sins and put them in a bag. Well, so we come over here, and so we have this, oh, mercy. Got these u's, du's. I cannot use something to represent the same something. Oh, no problem. Perhaps I didn't catch that so early in the morning. So let's use t, then dt. So negative dt. Do that. So here the du is represented, or the sine du, sine u du, that's the numerator, is represented by negative dt. So put the negative there, the integral. I'm going to say this is 1 over t. T represents the cosine. And then here the dt, or the negative dt, represents sine u du. So according to up above, the theorem that the integral of 1 over x dx is the natural log of the absolute value of x. Well, here it's t. So here we have negative times the natural log of the absolute value of t plus c. But t is cosine. So we have, just take it from the top. So the integral of tan u du is negative the natural log of the absolute value. Here t is the cosine u plus c. So I mean, that's the proof there that the integral of tangent u du, or tangent x dx, is the negative natural log of the absolute value of cosine if it's x plus c. And the proofs of the remainder is the same. The proof of the secant being the natural log of the absolute value of secant u plus tangent u is a little bit tricky. There we multiply by a sophisticated 1, and you can get the results, but I will not bother with that at this time. Let's look at some problems in this section to see if you can gain some pretty good knowledge of what's going on. So with this one, let u equal to x plus 1. We're using this very fantastic property that the integral of 1 over u du is equal to the natural log of the absolute value of u plus c. And is this the fat boy? No, it's not the fat print, but it looks like it's fat. So here, du is just dx. So this is the integral of 1 over u du, which that gives us the natural log of the absolute value of u plus c, but u is x plus 1. So we have here the natural log of the absolute value of x plus 1 plus c. So you got to be particular about that and make sure that you see what's happening. Number 5, there's a scalar, a fraction that comes out, and you want to be aware of how it shows up. Let u equal to 2x plus 5. So du is 2 dx. To represent the 1 dx, we simply here divide both sides by 2, so we have 1/2 du is equal to dx. So I come over here, 1/2 du represents dx, but I put the 1/2 out in front. That's the fraction. The integral of 1 over here, u is set to be the 2x plus 5. And then du, or 1/2 du, represents the dx, right? 1/2 du. Took my sins and put them in a bag. And then he sewed up the bag. Never to allow my sins to steal that which he has committed for me against that day. Well, this is 1/2 times the natural log of the absolute value of u. You can just go ahead and just put in what u is, which is 2x plus 5, and it's plus c. So the answer is 1/2 times the natural log of absolute value of 2x plus 5, then plus our constant. Don't forget that constant. That'll cost you. Now, why do we use the u du for the natural log? Here's the thing, and I should have said it here, the previous two problems. If your denominator, if its derivative gives you a form in the numerator, then use the 1 over u du to get the natural log of u. So look at number 3. U was x plus 1, du is dx. That's our numerator. Number 5, u is 2x plus 5. Du came out to be 2 dx. Well, 1/2 du represents the numerator. And so the same thing. If you let u here equal to x squared minus 3, du will pick up that x dx in a fraction, but that's fine. It's easy to deal with a number. Sometimes it gets tricky to deal with a variable. So let u equal to x squared. I tell you, my 2's. The 2's don't like me. X squared minus 3. That's a little bit better. Du is 2x dx. So the numerator is x dx. So obviously dividing both sides by 2, we have 1/2 du gives us the x dx. Now we don't need this, but that's what we use. So we'll just put that in a box. So this is 1/2 here, right? The 1/2 du represents the x dx, right? It's the integral of 1 over u du. So you kind of see what's happening. This is 1/2 times the natural log of the absolute value of u, and u is x squared minus 3. X squared thinking of a 3, x squared, slow down, minus 3, and then plus c. All right, that's not bad. Doesn't matter how it looks, you still use the same concept to tackle even, apparently sometimes, even trickier, difficult problems. Look at the relationship. This is x to the fourth, 3x. Take the derivative of that, I get some form of x cubed plus a constant. This is x cubed plus the constant. So, and that constant happens to be a 3, so we may be in the house. So let u equal to x to the fourth plus 3x. So du is 4 x to the third plus 3. This is all with respect to dx. So du picks up the numerator precisely. This is the integral of 1 over u du, which is the natural log of the absolute value of u plus c. And u is the x to the fourth plus 3x. Now this is pretty cool. You take this guy, if you have, anytime we have a plus b divided by c, well, you can simplify that just using arithmetic. This is a over c. That's not the c that I wrote, I'll tell you. Plus b over c. Well, we use that here. This is the integral of x squared over x minus 4 over x dx. Now that x squared over x can be simplified to just x, so this is the integral of x minus 4 over x dx. Now, if you see the answer, you just integrate x, you get 1/2 x squared, and then this becomes minus 4 natural log of x plus a constant. But I'll break it down. So this is the integral of the difference is the difference of the integrals, right? So this is the integral of x dx minus 4 times the integral of 1 over x dx. Well, that's a skinny 4, which I do not complain. So here we have 1/2 x squared. You just integrate that directly, minus 4 times the natural log of the absolute value of x plus c. Well, let's look at a few more. Well, it looks like it's a whole lot going on, but still same argument. It looks like we can use 1 over u du, and then we get the result being a natural log. Why is that? Well, you look at x cubed, take its derivative, we get x squared. Look at x squared, take its derivative, we get x. Look at the x, we take its derivative, we get a constant. So we may be in the house. So let's check. So let u equal to x to the third plus 3x squared plus 9x. So du is equal to 3x squared plus 6x plus 9. This is all dx. Now that numerator is that times a factor of a 3. So let's see. This is, look at it. This is du. We can factor out a 3 here. This is x squared plus 2x plus 3 dx. Well, that's the numerator. So 1/3, yes, du is x squared plus 2x plus 3 dx. So the 1/3 du represents the numerator with the differential So this is equal to 1/3 times the integral of 1 over u du. The u is the denominator. So here we have, we'll put that in a box. So this is 1/3 times the natural log of the absolute value. Just write the answer. The absolute value of u is x to the third plus 3x squared plus 9x. This is plus constant. All right. Now, look at the difference between this problem here where the numerator, its power is less than the power of our denominator. So we think 1 over u du to get the natural log of u. Here, the numerator, its power is greater than our power in the denominator. And telephone call. They have to wait. I did hang up. I didn't want to be saying that and they could hear me. Well, it's not my wife. If it was my wife, well, would I answer? Well, okay. Anyway, this is x to the third. The power here is 3. The power in our denominator is 1. So what do? Well, here's what you do. Anytime you have an integration, an improper fraction, you always divide it. What is the improper fraction? An improper fraction is where the numerator, the power of the numerator is greater than or equal to the power or the degree of the denominator. Okay, so if it's an improper fraction, you want to divide. And I think that was something that we learned dealing with numbers, the principle of numbers from grade school, improper fraction, right? 5 over 2. So you say that this is 2 1/2, right? You divide the denominator into the numerator to simplify it. Well, what about 6 divided by 6? It's also improper when the degree of the numerator is greater than or equal to the degree of the denominator. So that's why you just say that's 1. You don't walk around saying, okay, x divided by x. Well, just say 1, right? Well, so it is with numbers, so it shall be also with algebraic expressions. So if we have an improper fraction, the goal then is to divide. So we have x minus 3 divided into, and a lot of times you check to see if you can factor the numerator. Since this is a cube and this downstairs is x to the first, I'm just going to go ahead and divide. We're missing a term, so we inject a 0 there for it to hold the pivot spot in the mathematical chain of events. The algorithm, how we program computer software to run algorithmic functions, which is everything that generates the computer, whether it's C++ or Fortran or basic Mathematica, Maple, MATLAB, is looking for something in that position. It's expecting something. So here it expects, if it reads x to the n is 3, then it expects to see x to the second, it expects to see x to the first, it expects to see x to the 0. So we put something in that place. But anyway, x goes into x cubed x squared times x is x third, minus x squared times minus 3 is negative 3. Daggone it. X squared, we draw a line, subtract, it becomes negative, becomes positive. Well, here we get 0, we bring down the next term, which is nothing, right? And so we bring down the next term after that, which is something. Well, can x go into 5? No. So here we have x squared plus 5 over x minus 3. So this fraction reduces to that. So this is the integral of brackets x squared plus 5 over x minus 3. That's dx. Just integrate directly. So we get 1/3 x to the third plus 5, which is just a constant or just a multiplier, times this is the integral of 1 over x minus 3. And if you let u equal to x minus 3, du is dx. So this is just 1 over u du. So this becomes 5 times the natural log of the absolute value of x minus 3 plus c. Now let me tell you this. If this was a 2x right here, then this would be 5 over 2 times the natural log of 2x minus 3. If this was a 4 here in front of that x, then you have a fraction of a 1/4, right, for that u du. Substitution. So if it was a 4 there, this would be 5. That 5 carries over 4 times the natural log of 4x minus 3. If it was an 8 times x, it would be 5 over 8 times the natural log of the absolute value of 8x minus 3. So I think you get the idea. Oh, this is a really good one right here. You see this guy, even in calculus 2, it'll keep popping up. Matter of fact, same problem really. So first, you can simplify this x to the third. That 3 can come down as a multiplier of the natural log. So you can write this as 1/3 times the natural log of 1 over x, the natural log of x dx. It just helps us in trying to simplify this form. Now here's what you want to try to put the pieces of the puzzle together and make sure that they relate. The natural log of x, its derivative, its derivative picks up the 1 over x, because if you let u equal to natural log of x, du is 1 over x dx. There you go. So you always, in combat, the art of combat, whether it's martial arts, we're taught, and I haven't done that in years, but we're taught that if you're in a fight and there are several people you got to fight, you should be able to take them all. The first thing you want to do is identify the strongest component, and then you attack him. You get him first, even if it's a gunfight, right? Well, I know I shouldn't be saying that to you, but I'm just saying, if it was, you take out the greatest threat, and then after that, you deal with the others. So here our greatest threat is that natural log of x. So I deal with him, and once I deal with him, then the aftermath of the unscourge picks up whatever remains. So let's see. So let u equal the natural log of x. Du is 1 over x dx. Remember we talked about the derivative of the natural log of x in the previous section. This picks up everything that I need. So this is the 1/3 times the integral. Here, the u is this natural log of x. Du is the 1 over x dx. So I have 1 over u du. 1/3 du. Well, 1/3 is just there from this 3 here. We just brought it down, right? Put it in the front of the natural log, which, according to the associative property of multiplication, is the same as putting the 3 in front of the x times the natural log, right? So here we have 1/3 times the natural log of absolute value of u plus c. But u, is the natural log. Isn't that pretty? This is 1/3 times the natural log of absolute value of the natural log of x plus c. Okay, good stuff. Now this natural log of x, there's no absolute value around it. We have the absolute value from the rule, right? I'm just going to put that in parentheses. Doesn't matter, but I just want to put a coat on him. He told me the X said he was kind of cold. Okay, anyway. Oh, there's one more down there too. Okay, good. Now, this is tricky. One thing I know about this x to the 1/3 is that its derivative will pick up this x to the 2/3. What about that 1? Well, Dad Blabbit, just want to say that. Thought that sound cool. Let u equal to 1 plus x to the 1/3. The du, that 1 will go out in the derivative, right? So it's not in the way. So let u equal to 1 plus x. In the substitution, everything that is given must be substituted in some kind of way, right? You just can't leave anything just out there hanging. I'm not going to touch it. But you better get it, right? You have to take the oversight. That's right. So look, we're going to manipulate this problem, right? Amen. Okay, anyway. So let u equal to that. So du, the derivative of 1 is 0. And the derivative of x to the 1/3 is 1/3 times x to the 1/3 minus 1. That's negative 2/3 dx. Oh, so look, so 3 du is equal to 1 over x to the 2/3 dx. Wow. Doesn't that pick up everything you need? Okay, we got to move on. Try to keep these lectures to around between 20 and 30 minutes. I don't like to go over 30 minutes, so don't want to talk too much. So 3 du represents the 1 over x to the 2/3 dx. All right, 1, 2, 3. 1, 2, 3. So this becomes 3 times the integral of 1 over u. What's u? U is this 1 plus x to the 1/3. And then the du, right? 3 du picks up everything else. So this is 3 times the natural log of the absolute value of u plus c. This is 3 times the natural log of the absolute value. U is the 1 plus x to the 1/3 plus c. Okay. Well, we need to know something about the derivatives of cotangent and secant. So the derivative of cotangent is negative cosecant squared. So we need that. So let's see. Let u equal cotan t. So du is negative cosecant square t dt. So negative du represents our numerator, cosecant square t dt. So this is negative times the integral of 1 over u du. All right? The 1 over u just represents 1 over cotangent t, and du, negative du, right, picks up the cosecant square t dt. Just write the answer. This is negative times the natural log of absolute value of u. U is the cotangent t plus the constant c. Well, oh boy, I think that's it. 29 minutes.